A linear transformation in 3 dimensions sends infinitely many input vectors to infinitely many outputs, yet just 3 pieces of information pin it down completely. Watch this cloud of arrows collapse to only 3 special vectors, the bases. That's the entire transformation, encoded. Today we uncover why and the hidden choice lurking behind every coordinate you've ever written. Let's start with what a basis actually is. A basis is a minimal set of vectors that spans the whole space. In an n-dimensional space, you need exactly n of them. Here's the crucial property. Every vector v can be written as a unique combination of basis vectors, that is, v equals c1 times v1 plus c2 times v2 all the way through cn times vn. Those coefficients, c1 through cn, always exist, and they are unique. No other combination of the basis vectors produces the same v. Now apply t to both sides. Linearity gives us 2 rules. First, t of a sum equals the sum of the t's. Second, t of a scalar times a vector equals that scalar times t of the vector. Let's push t through the expansion. The sum splits apart using additivity, and then the scalars slide out using homogeneity. We're left with t of v equals c1 times t of v1 plus c2 times t of v2, and so on, plus cn times t of vn. Same coefficients, new vectors. The transformation is fully reconstructed from just its action on the basis. Let's make this concrete. Take t to be a 90-degree rotation in the plane. We only need to know what it does to the standard basis. T of E1, the vector 1, 0, rotates to 0, 1. T of E2, the vector 0, 1, rotates to negative 1, 0. That's it, just 2 outputs. Now take any vector, say v equals 3, 2. Decompose it, v equals 3 times E1 plus 2 times E2. Apply our formula from before. T of v equals 3 times t of E1 plus 2 times t of E2, which is 3 times 0, 1 plus 2 times negative 1, 0. That gives 0, 3 plus negative 2, 0, which equals negative 2, 3. The rotation computed without ever rotating v directly. Notice what those coefficients really are. When we wrote v as 3 E1 plus 2 E2, the numbers 3 and 2 are the coordinates of v. Coordinates aren't stamped onto a vector by nature. They're invoices written in the currency of whatever basis you chose. Change the basis and the invoice changes. But the vector, the actual arrow in space, hasn't moved. This distinction is the secret hiding in plain sight inside every tuple of numbers you've ever seen. Here's the punchline. When you write a vector as 3, 2, you're silently assuming the standard basis. The notation means 3 times E1 plus 2 times E2. That's a convention, not a truth. Pick a different basis and you get different numbers for the exact same arrow. Take this fixed vector. In the standard basis, it's 3, 2. Now switch to a new basis. V1 equals 1, 1 and V2 equals 1, negative 1. The same arrow now decomposes as 2.5 times v1 plus 0.5 times v2. You can check it. 2.5 times 1, 1 is 2.5, 2.5, and 0.5 times 1. Negative 1 is 0.5, negative 0.5. Add them and then you get 3, 2, the original arrow, so its coordinates are now 2.5 and 0.5. Same arrow, different language. A common reflex is to think. Isn't 3, 2 just what the vector is? No, it's what the vector is relative to E1 and E2. The arrow itself is geometric, a length and a direction in space. The numbers are just bookkeeping in a chosen language. Drop the basis and the numbers lose their meaning. This is why mathematicians say a vector lives in the space, but its coordinates live in a basis. This reorganizes everything. A matrix is just a table that records where the basis vectors go. The first column is t of v1. The second column is t of v2. That is the entire content of the matrix. Change the basis you record in, and you get a different matrix for the same transformation. The transformation itself has not changed. only the dictionary you are using to describe it has. Choose the right basis, and the tangled transformation can look like pure scaling along each axis. That's diagonalization, and the special basis is the eigenvector basis. So here's the closing thought. A linear transformation isn't its matrix. A vector isn't its coordinates. Both live underneath the numbers. The basis is the dictionary that translates between them.